Hi everyone, welcome back. Today we're going to be working on Computer Network Fundamentals, Chapter 3, Ethernet. Quick history on Ethernet. It was developed in 1973 by Xerox. The transfer rates were initially 3 megabits per second. These three companies eventually partnered up to work on it, and so in 1979, that's when that happened, and they got speeds slightly improved over the previous version of 10 megabits per second. Eventually, they would transfer control over to the IEEE, the Institute of Electrical and Electronics Engineers. This is going to be something that comes up a lot in this class, so it's good to remember what that is. At this point, it became an open standard, 802.3 standards. Last week, or in chapter 2, we talked about how there's several different 802. Whatever standards. So there's .3, .5, .11, etc. There's a whole bunch of different categories that each focus on a specific thing. Right now, we're going to focus in on this .3 standard, which is entirely built around Ethernet. So IEEE 802.3 is a working group and a collection of standards defining the physical layer and data link layers media access control MAC of wired Ethernet. So again, we're primarily focused on layer 1 and layer 2 of wired Ethernet. As technology progresses, there's been the need for variations of the 802.3 standard. So we have a list of some of them right here. This is not all of them, but feel free to take a moment to look through that. You can also go to the Wikipedia page, and there is a massive list of all the variations of the 802.3 standards available. This chapter primarily focuses on layer 2, the data link layer, and layer 1, the physical layer. I wanted to take a second to kind of zoom out and take a look at the big picture. We're not going to go into a ton of detail here. You don't have to remember every little bit of this. We're just, again, going to try to look at it at a glance. And then later in the semester, we're going to look into each one at a closer level. When we're trying to communicate with another device, layer 7, 6, and 5, the application, presentation, and session layer will create something called a payload. That payload will then be passed on to layer 4, where we will add a header to it. So we'll encapsulate the payload and add a header to it. We'll call this a segment or a datagram, depending on the situation. We'll talk more about that later. And then we will, that header will have information for how things at the transport layer should deal with it, like firewalls, port numbers, all that kind of stuff. Again, we'll dig into that later. Then this will be again passed down to layer 3, where we'll encapsulate that and put another header on it. We'll call this a packet. So at layer 3, we call it a packet. And this header will have information like IP numbers, IP addresses that tell layer 3 devices how they should interact with this. So routers, things like that. The next thing that will happen is this will be passed on down to layer 2. Something slightly different happens here compared to the other layers. So when we encapsulate this, we encapsulate the previous headers and payload, we add a new header and something called a trailer. And then we call this a frame. So at layer 2, we're going to call that a frame. Device that we're working with on layer 2, it's going to be something like a switch would be an example of that. Going to talk about frames in a little more detail here in a second. Again, I just wanted you guys to have the kind of bigger picture context. So again, the idea is that when we want to communicate with another device, it'll create a payload. It will pass that down in a process we call encapsulation. We'll add different addressing information at each layer. So at layer 4, we're going to have something like port numbers. Layer 3, we're going to have IPs. Layer 2, we're going to deal with MAC addresses. At each layer, we give it a new name. So we call the whole thing, usually it'll be like a payload or PDU sometimes throughout the whole process, but we give each layer a specific name. So layer 2, we call it a frame. Layer 3, we call it a packet. Layer 4, we call it a segment or a datagram. Again, depending on the situation, we'll talk more about that later. Example of devices that we may work with at each layer. So layer 1, you would have something called a hub. Layer 2, you'd have switch. Layer 3, you'd have a router. Layer 4, you deal with things like firewalls. Okay, so that's a kind of quick look at the big picture of the OSI model and this kind of network communication process. Let's dig into layer 2 and layer 1 a little more when we talk about Ethernet. Okay, layer 2 of the OSI model, we're going to deal with something called an Ethernet frame. The parts of a frame are the destination address, the source address, the type, the data, and the FCS. So this is kind of a visualization of what a frame might look like. We have all this different information in here grouped into a section. Let's go ahead and look at the different pieces a little bit closer. So the destination and source addresses are MAC addresses, as we just talked about a second ago. So we're dealing with at layer 2, we're dealing with frames, and we're using something called MAC addresses at layer 2. Again, here's a quick recap on MAC addresses. It's layer 2 addressing. They're 48 bits long, 12 hexadecimal digits. Traditional MAC addresses contain 2 parts. The first 20 bits are the OUI. The last 24 bits of the device are the device ID. And this, again, is an example of what a MAC address might look like. So that is the first 2 parts, the destination MAC address and then the source address. After that, we have the type. The type is just information sort of about what's going on at the layer above it, whether it's going to be IPv4, IPv6. That's kind of the bulk of what's going on with type. The last section here is the data section. So this will include our payload and the other encapsulated data that we talked about just a bit ago. You can also end up with padding. So a frame must be 64 bytes in size. So it has to be a total of 64 bytes. So if you have information that doesn't quite fill that up, they will add in padding to fill out the rest of that information. The padding is added by the NIC. The last section we have here is the FCS. FCS. This stands for Frame Check Sequence. This stands for Frame Check Sequence, FCS. The kind of short version of it is when we want to communicate with another device, we want to make sure that frame is sent in its entirety. We don't want it to be damaged or information to be lost along the way. So the way we do it, or the way devices handle that, is they do something called a CRC, cyclic redundancy check. The sending device will do a special mathematical calculation and get a long string of numbers. And then whenever an intermediate device handles this frame, it will do a calculation and see if it gets the same number. If the numbers match, everything is fine. If the cyclic redundancy check fails and the frames don't match, then there's a special process that will be carried out. We'll talk about that later on. 10BASE-T. It was created by the IEEE in 1990. It's for whenever you have 2 or more devices connected to a central hub. This was the speeds that it was built to deal with, 10 megabits per second over twisted pair. The name comes from the signaling type, which was baseband. It was the cable carries only one signal, and then the T comes from the cable type, twisted pair, UTP. 10BASE-T required Cat3 cabling or higher. We don't really use, it's kind of an obsolete, outdated standard, but one pair of wires sent data, the other pair of wires received data. So generally you would have a cable with 8 wires still, so you'd have 4 pairs total, but we're just only using half of them. It was the first connector to use the RJ45 connector, or as the first cable type to use the RJ45 connector. Okay, this next one is kind of a big one. When we have our twisted pair wires, they have to go into the connector in a specific order in order for network communication to work effectively. We have 2 standards for that, the 568A standard and the 568B standard, or the long version TIA EIA 568A or the TIA EIA 568B. So we have an example of the 568A standard on the left here, and we have an example of the 568B example standard over here on the right. The order, we absolutely have to memorize this. This is something that's going to be super important. The nice thing is you only really have to memorize one pinout. So if you remember 568A, the pinout for this one, so if you remember the pinout for 568A, all you have to do to change over to the B standard is switch the green and orange wires. That's it. So it's exactly the same except for the green and orange wires switch places. I think your book recommends remembering the term go, green, orange, to remember the difference between 568A and 568B. Quick summary of the 10BASE-T. We have speeds of 10 megabits per second. Signaling type is baseband. The distance is 100 meters between the hub and the node. The node limit is no more than 1024. The topology it's designed for is a star bus topology. The cabling type is Cat3 or better UTP cabling with RJ45 connectors. We have another standard that we're going to dig into, 10BASE-FL. This is primarily for fiber optic. So it's not the super fast fiber optics that we're dealing with nowadays, but it's one of the earlier iterations of a fiber optic standard. Again, just a recap on some of the advantages of fiber optic. Optical signals can travel farther. Fiber is immune to EMI, and fiber optic cables are much harder to tap into. Okay, this is a quick summary of that. The speed is still 10 megabits per second. The signaling type is still baseband, but our distance has increased significantly here. Now we can get 2,000 meters between the hub and the node. The node limit, again, same as before, 1024. The topology, same. And then the cabling type changes. CSMA/CD. This stands for Carrier Sense Multiple Access with Collision Detection. Essentially, the first part of this means that we have multiple devices on a network. Each device has equal access to the network. Sort of works in a first come, first served basis. Each device will attempt to sense whether the network is free for communication, whether they can send a signal over the wire. Once a device detects that the line is open, it will attempt to send its data over the network. Sometimes what will happen is multiple devices will attempt to send information. We have a collision. That's where this part right here comes in. CSMA/CD allows for the network to detect that a collision occurred and attempt to resolve that issue. The way the network will attempt to resolve that issue is the devices that were involved in the collision will sort of roll a random number, and then it will attempt to wait that long and then check to see if the network is open again, and then attempt to resend its signal. So that's how it deals with collisions. The trouble with hubs. Hubs could only have one message on the wire at any time. Performance dramatically decreased as more devices were added. Switches, on the other hand, are smarter than hubs. They use MAC addresses to manage traffic. Switches allow each device full bandwidth. So if this were a hub in the center and not a switch, how this would work is when this device attempts to communicate, it would send the message onto the hub, and then the hub would broadcast that to every other device on the network. What a switch will do is, at least once it's established its MAC table, once it knows where every device is located, when this device wants to communicate with a device over here, it will attach that MAC address to its frame. So it will send this information out to the switch, and the switch will say, I know where that device is, and it will forward it to the target, only the intended target. So instead of broadcasting it out to everyone and flooding the entire network, it will manage that traffic efficiently and intelligently. Again, at layer 2, switches work at layer 2. And they deal primarily with MAC addresses. Connecting Ethernet segments. We use something called, or at least at one point in time, they use something called an uplink port. It would enable you to connect multiple switches together using a straight through cable. So this is an example of what an uplink port would look like. Modern switches have something called auto sensing, MDIX. Modern switches do not have a dedicated uplink port. Modern switches, again, use that auto sensing feature. Crossover cable. Again, this is something you're probably not going to see a whole lot of in the real world, but it definitely comes up as a test question here and there. So a crossover cable reverses the sending and receiving wires. The crossover cable connects to a regular port on each switch. Modern switches don't use them because they have auto sensing. Spanning tree protocol. So this one is a little bit complicated. I'm going to try to make it as straightforward as I possibly can. It is a layer 2 protocol. It's designed to prevent loops. So let's go ahead and dig into that. Sometimes you may have a set of switches for multiple networks that create a loop. So we have a loop here, we can see. There are certain situations where a switch might need to broadcast out in every direction. So let's say switch A here broadcasts out to C, B, and D. There are certain situations where that broadcast would then be forwarded by the next switch in all directions. So C would broadcast that back to B, back to A, every direction. B would broadcast that in every direction, again, back to A, back to C. And then each of those will then forward that again back to A and back to B, back to C, and back to A. So again, it's just kind of bouncing that around in the loop in all direction. And our initial switch here that sent out one broadcast now received two, and then it will then forward both of those back out, and eventually that will come back as 4, and so on and so forth. And so a single broadcast can end up becoming an infinite number of broadcasts. They call that a broadcast storm. Essentially how it works is it will restrict traffic. So it will designate one of these switches as the root bridge, and then it will disable the ports on the other one. So let's say switch A was designated as the root bridge. It was elected as the root bridge. It will then disable this link between B and C. So instead of having a loop, we have a tree for communication. It's not permanently disabled or kind of hard disabled. It's more of a soft disabled. If something were to happen, the network were to change, or one of the other routes of communication were to be disabled, it will open that back up for communication. So it will use something called a topology change notification. The last thing that we're going to look at here is something called root guard. So these are all part of the Bridge Protocol Data Units, BPDU. So we talked about the root bridge, we talked about the topology change notification. The last one we're going to talk about is a root guard. And the short version of that is it's basically a protocol that prevents an unwanted switch from becoming the root bridge. So it helps to prevent unwanted switches from becoming the root bridge. So in short, the spanning tree protocol prevents loops and broadcast storms. All right. Thank you all for joining me. That concludes chapter 3 on Ethernet. I hope you all have a wonderful week.